So we're now going to discuss enantiomers, and this is from the isomerization and stereochemistry chapter. And we'll start by looking at some definitions of chiral centers and enantiomers. And a molecule containing a tetrahedral carbon bonded to 4 different groups is called a chiral compound. And so, for example, here we have alanine, the carbon atom in the middle of alanine is bonded to 4 different groups, an amine, a carboxylic acid, a methyl group, or CH3 and a hydrogen. So the carbon atom in the middle of alanine is indeed chiral. The tetrahedral carbon atom is called a chiral center or stereogenic center, and the 3D arrangement of groups around a chiral center is indicated using hashed wedged line notation. So for example, this structure here shows one enantiomer of alanine, and the big fat bond to the methyl group is the wedged line, and that's pointing towards us, and this hashed line here to the hydrogen is pointing away from us. A chiral compound and its non-superimposable mirror image are called enantiomers. So here are the 2 different enantiomers of alanine, and as you can see they are mirror images of one another. And this is the so-called S enantiomer, and this one here is called the R enantiomer. And we'll look at how we can define the terms R and S enantiomer in a minute. It's very important that you're able to spot chiral centers in organic compounds, and so we'll look at 3 examples. The first one is a naturally occurring amino acid called cahnic acid, and if we look at the structure of cahnic acid, we can see there are 3 chiral centers in this molecule. One here, another one here. So we've got 3 chiral centers in total. If we look at a more complicated structure, lovastatin, if we count the number of chiral centers here, there are actually 1, 2, 3, 4, 5, 6, 7, 8 chiral centers in this molecule. And finally, resveratrol, if we look at the number of chiral centers in this molecule, you'll see that there are actually none at all. And so this is described as an achiral organic compound. So we're now going to look at assigning RRS configuration, the so-called Cahn-Ingold-Prelog Nomenclature. And to do this, we're going to look at an example, and this is one enantiomer of alanine that we saw earlier on. We're going to define this as either R or S. And the first thing we need to do is to rank the atoms around the chiral carbon atom. We're going to identify the highest and the lowest priority groups. And so when we look at this enantiomer, we find that the nitrogen has the highest priority group and the hydrogen has the lowest priority group. And the reason for this is because we are prioritizing the groups around this chiral carbon by atomic number. Nitrogen has a higher atomic number than carbon, so it's a higher priority than these 2 groups, which in turn has a higher priority than the hydrogen. Now what we need to do is to prioritize these 2 substituents here, the carboxylic acid versus the methyl group. And to do this, we're going to use what's called the first point of difference. This carbon is bonded to 2 oxygens, this one is bonded to 3 hydrogens, so we're going to prioritize those 2 groups. And when we do that, we see the carboxylic acid group here has a higher priority than the methyl, and that's because the oxygen atom has a higher priority than hydrogen. So as a consequence of that, the carboxylic acid is the second priority group. All that remains now is to draw a curved arrow from the first to the second to the third priority group, but ensuring that the lowest priority group points away from us, which indeed it does in this particular case. So here is my curved arrow, and as you can see, the arrow is going anti-clockwise. As a consequence of that, this is the S enantiomer of alanine. So this is the S enantiomer. If we look at the other enantiomer of alanine, which is this one here, that's the R enantiomer. We're now going to look at enantiomers with more than one chiral center. So let's look at cahnic acid again, and if we define the stereochemistry, or if you like, the configuration of each of those 3 chiral centers using the R and S system, you'll find that all 3 chiral centers have S configuration. If we look at the mirror image of cahnic acid, which is shown here, the enantiomer, if you look at the configuration at all 3 chiral centers, you'll see that these have the R configuration. And it's very easy to compare the structural similarity between these two enantiomers if you flip over this particular structure of the enantiomer to give us this structure here, and you can see that all the three substituents are in a different orientation in the enantiomers. These two groups are pointing away from us, whereas in the enantiomer they're both pointing towards us. The carboxylic acid in the S enantiomer is pointing towards us, and the R enantiomer is pointing away from us. So we can see here that for the enantiomer, all three of the chiral centers have the opposite configuration. Let's now finally compare enantiomers versus diastereoisomers, and again we'll look at cahnic acid. We've just now seen that the enantiomer of cahnic acid has the RRR configuration, so the enantiomer has a different configuration at all three chiral centers. Let's now look at a molecule with a different configuration at just one of the chiral centers, namely this molecule here. And you'll see that the chiral center at this position here has R configuration rather than S. The other two chiral centers have the same configuration. When one configuration is different but the other two are the same, then this is called a diastereoisomer of cahnic acid. It's actually given the name allocahnic acid. If we change two of the chiral centers to a different configuration, in this case top two RR from SS, you get another diastereoisomer of cahnic acid. This chiral center here has the same configuration as cahnic acid. These two are different. So in terms of a definition, a diastereoisomer is a different configuration at one or two of the chiral centers.